Hey guys, in this video we're gonna continue to study in some theorems about integrability of a function. And remember in the last few videos I've introduced that the criteria for integrability. It says that a bounded function is integrable if and only for any epsilon you can find a partition corresponding to that epsilon, such that the difference between the upper integral and the lower integral is gonna be smaller than epsilon, right? And we can actually rewrite this criteria in another way, a way that uses the sequence of a partition. So it's stated like this: a bounded function is integrable on AB if and only if there exists a sequence of partition Pn, and from 1 to infinity, right? A sequence of Pn satisfying the limit. If you are taking the limit of the difference of upper integral and lower integral, it's going to be 0, right? And I said that it's actually the same thing because for the criteria that we introduced before, we said that for any epsilon larger than 0, you can find a corresponding p epsilon, right? So then if I am taking a sequence of epsilon and let the epsilon goes to closer and closer to 0, then there's gonna be also a corresponding sequence of partition p epsilon, right? And I said that, and in the criteria we know that the difference of the upper and lower integral is going to be smaller than epsilon. So when epsilon goes to 0, the limit, if we are taking the limit of the sequence of epsilon, then the difference is going to be smaller or equal to epsilon, and epsilon goes to smaller and smaller. So if you are taking the limit, the difference is going to be 0, right? But still, I'm going to show you guys some idea on how to prove this theorem. So first of all, assume that we already have a sequence of partitions. There exists a sequence of partitions Pn satisfying limit and goes to infinity. The difference of upper and lower integral is going to be 0. Then we want to show that the bounded function is actually integrable. Right, so then to show it's integrable, we use the criteria for integrability. So then given any epsilon larger than 0, we can actually choose Pn from this sequence Pn, right? And choose a Pn such that the difference between lower and upper integral smaller than epsilon, that the epsilon that you choose. Sorry. You can always find such Pn, right? Because the difference of UF and LF is gonna be 0. It's gonna be smaller and smaller. And for any epsilon, you can always find such partition, right? I think I made a mistake. Sorry. It's not supposed. They are not supposed to be upper and lower integral, but upper and the lower sum, because now you see UF and LF are dependent on the partition you choose, right? So I made a mistake. Just now I was thinking if I'm gonna redo the video, but actually it's not a bad thing for you guys to know that I made a mistake like this, because sometimes sometimes you are not aware of possibility of making such mistakes until you you yourself made mistakes, or you find someone else made the mistakes, right? So, well, just a notice for you guys that here UFPN and AFPN represents the upper and lower sum, not upper and lower integral. Right, sorry about that. Okay, so then now we've shown that we've shown the sufficiency of the theorem, and then we're gonna show the necessity of the theorem. So now, if we are given a bounding function that is integrable on AB, we want to show that there exists a sequence of partitions satisfying the limit condition, right? Okay, so now suppose f is integrable, and then by the criteria of integrability given epsilon, for any epsilon, right? Suppose given epsilon, so when we say given epsilon, it's like already fixed an epsilon, right? And we call it epsilon n, because we can actually construct a sequence of epsilon. You just take one epsilon at a time, right? Okay, so given epsilon n, you can since f is integrable, we can actually find Pn corresponding to epsilon n, such that UFPN minus RFPN is smaller than epsilon, right? But that's not enough. We wanna show that the difference of UFPN and RFPN is actually going to 0. So what we know that is that the difference is gonna be smaller than epsilon n, but epsilon n can be very small. How small can it be? We want to show we are taking the limit of epsilon, right? So when we choose epsilon, we can actually choose it in a smarter way. We choose it. We can choose it to be like choose it to be like, say, XPN larger epsilon n larger than 1 over n, so that in this case smaller. So that in this case, epsilon n is gonna be smaller than 1 over n, right? And 1 over n is going to be 0 when n goes to infinity, right? Because we are actually taking the limit of epsilon n, or the limit of 1 over n. And and the way we choose epsilon n is correct, or it's robust because, well, for n larger than 1, then epsilon is going to be smaller than 1, very small numbers, and n can't be smaller than 1, right? N is a integer, positive integer, and it is also the way we want, and we want the epsilon n to be, because we want to take smaller and smaller epsilon, right? And when n goes larger and larger, then epsilon n is gonna be smaller and smaller, right? Okay, fine. So now, if we're taking the limit of n, then this part will be equal to 0, right? The limit of the difference is gonna be 0, as desired. So now we prove that the theorem is true. Alright, now the second theorem I'm gonna show you in this video is about integrating functions with discontinuities. Well, remember I was in the last video I said that if a it's not what I say, it's the theorem says that if we're given a continuous function on the compact set, then the function is also integrable. But what if we are given a discontinuous function? Is it still integrable, or do we need some other conditions to support its integrability? So this theorem says that if f is bounded, it doesn't require f to be continuous, and if f is integrable on C to B for all C in AB, except C can be any point in AB except the endpoints, and then f is integrable on AB. And this is the same if we are taking the other endpoint. So if f is integrable on AC for all C in AB, then f is also integrable on AB. Well, since C can be all values except for the endpoint, so what we're really interested in and what is the most trickiest thing is at the endpoint. Suppose this is A and this is B, and suppose we have, this is a continuous function, but what if like the function is like this, the function at fa is not continuous, but we know that for C not equal to A, any point here, for any interval here, it's integrable, right? F is integrable. So we want to show that even if we include the point A, which the function where the function might be not continuous at this point, the function is still integrable. So where what we know now is that if take any point, say x1, then this part will be integrable, right? And we want to add one point A here, and we want to show the function is still integrable in this part. So I think it should remind you of the refinement, right? Because because refinement is kind of like adding one point. Sorry, not necessarily adding one point. You can add as many as you want, as long as the partition is finite, right? But here we just want to add one point. We're adding one point. So say the original partition is P1, and now the partition becomes P1 minus one point A, a single point A, and we want to show that the function is still integrable under this partition, right? So we can start from here. If we are given the partition P1, say this is X, so then what we know is that then UFP1 minus LFP1 is going to be equal to, by the definition, it's going to be equal to MK minus MK, the infimum, and this is a supermum, and this is infimum of the function at each small interval, times xk minus xk minus 1 is gonna be smaller than some epsilon, right? Not some epsilon, for any epsilon, right? And well, we can actually call it epsilon 1 because we're gonna use epsilon as well. So And here k is actually starting from 2, right? Because 2 to n, because we suppose this point is x1, but we are not taking x1 minus x0. We can actually set a to be x0, right? We're not adding this part because we're only considering x1 to be this interval, and f is f is integrable in this interval. So what will happen if we add a into our partition? Then here, if we are considering partition P, then UFP minus AFP is gonna be equal to M1 minus M1. Capital M1, small m1 is the supremum and infimum of function at this part in the interval a to x1. Okay, x1 minus a times plus the rest of the result of the partition. Okay, and this is gonna be smaller than where this part is epsilon 1, right? And this is gonna be smaller than m1 times x1 minus a. And we want to show actually this part is smaller than epsilon. And we might as well take epsilon 1 to be epsilon over 2. Or if you want to take a smaller number, it's fine. It doesn't matter if what value you are taking. It's just for I was just want to show you like prettier way of proving it, and it's quite usual for us to quite normal for us to set epsilon 1 to be epsilon over 2 or epsilon over like 3 if the final part is gonna be divided into 3 parts. Then we kind of like wanna make each part smaller than epsilon over 3, so then if you add them up, the whole term is gonna be smaller than epsilon. So we wanna make sure this part is also gonna be smaller than half epsilon. And what we can be sure is that m1 minus m1 can be smaller than something like 2m. It's quite natural to get this solution because we know that f is bounded. F is bounded on a b, right? So there's gonna be some m such that fx, absolute value of fx is smaller than m. So m1 minus m1, the supremum and infimum of the function in the interval a to x1 is gonna be smaller than 2 times m, the upper bound of f. So this part's gonna be smaller than 2m. So we actually want to get x1 minus a smaller than, if we can make sure x1 minus a is smaller than like 4m epsilon over 4m, then if you multiply it by the difference of capital M1 minus M1, so if we multiply it by this times 2m, then this whole part is gonna be smaller than epsilon over 2, right? So now we actually find such x1 that satisfies x1. If x1 satisfies this condition, x1 minus a is smaller than epsilon over 4m, then the result holds. The result actually holds, right? because actually x1 can take this is actually the difference between x1 and a, and x1 the distance can be even smaller, but you cannot take a x1 with distance between x1 and a larger than epsilon over 4m, because in that case you cannot prove that the difference between the upper and lower sum under the partition P is going to be smaller than epsilon, right? Remember, here, whatever x1 we take, we always have x1 to x1 to b. The function f on x1 to b, this interval is integrable. The only thing is that you're gonna find some point like say x1, and x1 can be very small because f is integrable for all on say b for all say in AB, but x1 cannot be a. Then how small it has to be to make sure that the whole function is the whole function is integrable. Sorry, the function is integrable on the whole interval AB. Then we'll find that x1 has to be this small, as long as the distance between x1 and a is smaller than epsilon over 4m, then the result holds. Alright. Okay, so then we if you write it the other way around, because we kind of like from the result, and we step by step and finally find what x1 is gonna be, right? And in when you prove it, you have to first claim that you have to first take some x1 such that x1 minus a satisfy the inequality, and then step by step with x1 minus a satisfy this inequality. What you will get? You will get that m1 minus m1 times x1 minus a is smaller than epsilon over 2, right? And then you also use f is integrable on the interval x1 to b. Then combine them together, you will find that f is actually integrable on AB. Right? Okay. So just notice that almost every function we are talking about when we are talking about integrability, these functions are bounded, right? And this is probably what Riemann integral about. We are basically talking about bounded function. But what if the function is unbounded? Then probably we might not be able to use Riemann integral. But we are not gonna cover this in these videos, and I think this is what I want to talk about in this video. And in the next one is gonna be some properties of the integral. Okay, so hope you enjoyed, and see you in next one.